we're trying to model what's called lifetime random variables. A variable that represents the lifetime of something. Could be a person. I have a newborn baby here. How long is this baby going to live? Okay. Of course, as parents, you want them to live as long as possible. You don't want to think about when they're going to die, because figuring out how long they're going to live is also implying when they're going to die. But for insurance companies, life insurance companies, they want to know information like that. How long is this person likely to live? But we also could, let's avoid thinking about people. We could think about the lifetime of light bulbs, batteries, appliances. Okay, let's think about refrigerators. So T is going to be the lifetime of an appliance, say, like a refrigerator. It is random. You sell a refrigerator to somebody, neither you nor they know how long that refrigerator is going to last. In the olden days, when I was young, 30, 40, 50 years ago, seemed like they were more built to last, maybe even sometimes 30 years. And now there's planned obsolescence, right? Things break easier, it seems. I don't know. Is that really true? Maybe, maybe not. So maybe more likely they'd last 10 years or something like that. It is random. It's a random variable. And notice I made it a capital letter. It is traditional to denote random variables with capital letters instead of lowercase letters. There's a good reason for that, as we're going to get to very soon. I might want to answer some questions. Number one, the most fundamental question, but perhaps the hardest question, is what is the distribution of this variable? What is the distribution of T? What do I mean by that? Well, a normal distribution is one possibility, bell-shaped curve. That's one possibility. That could be a density function, a probability density function, modeling values of T. How long is the refrigerator likely to last? Where the graph is higher, that's values of T that corresponds to data that's more dense. If you've sold thousands of refrigerators over many, many years, maybe you have a system, maybe it's an electronic chip nowadays, that keeps track of when the refrigerator dies, when it breaks down. And you keep track of that, and it's denser where the graph is higher. That's one possibility. We're going to avoid normal distribution in class today, though I might assign it on homework. Instead, we're going to focus on an exponential distribution, an exponential decay function, and pretend that's the distribution. I'm not saying that's accurate. I'm just saying it's one possibility. Whether a distribution is accurately reflecting reality or not is dependent on the situation and the data that you have. That's one question we could try to answer. A couple other related questions are, what's the average value of T? What is the average, more specifically, the mean of T? How long should a refrigerator last on average? That would be important if you think about it. Knowledge for the company to know, especially if they're going to insure the refrigerator, say with a lifetime warranty. And let's keep it real simple. Whenever that refrigerator dies, even if it lasts 30 or 40 years, they pay you $1,000 for a new refrigerator. Doesn't that sound like a great deal? Okay, yeah, it might be a great deal. But if that's going to be the case, if they're going to warranty it that way, they better be saving up money to pay everybody they sell refrigerators to. Okay, but just for the sake of keeping things simple, maybe let's go ahead and pretend that they do that. And we would want to know, how long do they last on average? But averages can be skewed by high outliers. maybe every once in a while, a refrigerator lasts 80 years. That's going to really skew the mean. When you add up those numbers and divide by the number of refrigerators you sell, one really high outlier is going to make the mean much bigger than what you would say is a typical refrigerator lifetime. So we're also interested in something else. What is the median lifetime? With data in statistics, hopefully you've known since 6th or 7th grade, the average, the mean, is what you get when you add up the numbers and divide by how many there are. Think about basketball games. Maybe you play basketball, okay? Maybe you played 20 games in the last season and you scored 180 points total for the season. What's your average? The total points you scored, 180 divided by the number of games you played, 20. 180 divided by 20 would be 9. You average 9 points a game. That's a useful measure of a typical game, you might say, though it doesn't take into account high outliers. Maybe there was one game where you got 40 points, and pretty much every other game you got like 4 or 5 points. Okay? The average could still be the same. The mean is greatly affected by that outlier, and the median is less so. The median is the middle number when you put the numbers in order from least to greatest. Whatever number is in the middle, or there could be 2 middle numbers. If the number of numbers you have is even, there's actually 2 middle numbers, and you might have to average those. We're not going to do the mean and median of data here. We're going to do the mean and median of distributions, more theoretical things here. But they are related to statistical data. And means and medians you'd compute for data. They're related. And we might want to know how much spread do we have? What is the spread? Or the best way people most commonly measure spread, especially if the distribution's symmetric, a little less so if it's skewed, like our example will be, is what is the standard deviation, it's called. Standard deviation of t. That's a measure of spread. And it's going to be related to another measure of spread called the variance. This is related to the variance of t. The variance is a little easier to compute and work with theoretically. The standard deviation is easier to interpret the meaning of. So we're going to think about these questions, both in the abstract and for a particular example. The particular example we're going to consider is an exponential distribution, which we've thought about before. Exponential distribution. The PDF probability density function is an exponential decay function. Although I'm going to be a little bit more picky about how I describe this PDF today. It's an exponential decay when t is greater than 0, and it's 0 everywhere else. And remember our main condition about a PDF that came up on the exam, and you should know for future exams, it's got to integrate to 1, representing 100% of the data, or 100% of the probability is another way to think of that. And with an exponential decay, when t is greater than 0, the formula we used was lambda e to the negative lambda times t. That's if t is greater than 0. You can either put a strictly greater than 0 or a greater than or equal to 0. It really doesn't matter, because the probability that t equals 0 exactly is 0, and so it doesn't matter whether that's greater than or greater than or equal to. Mathematica chooses a greater than or equal to, so I'll choose the same as Mathematica. It's 0 otherwise if t is less than 0. So technically the graph of this is discontinuous. It's 0 over here when t is negative, and then it jumps up here before it's an exponential decay. Its value at t equals 0 is lambda. That's the vertical intercept there. And remember what this represents. This is a model for data. Imagine you've got thousands of data points. and you plot them along this number line. Where the PDF is larger, where the probability density function is larger, the data will be more dense. In fact, the density over small intervals will be proportional to the height of the graph. Where the graph is lower, the data will be less dense. Every once in a while, you'll get a high outlier, but mostly the data cluster close to 0 here. Lower values of t, though that does depend on the value of lambda itself as well. How big, what it means to be close to 0 in that case. Does this really integrate to 1? We will use Mathematica a lot today to do calculations for us. This was a calculation we did before by hand. It's an improper integral. Improper integral from 0 to infinity. Lambda times e to the negative lambda times t dt. Mathematica, does this integral equal 1? Yes, with a caveat. Stephen Wolfram, who programmed Mathematica, created it from scratch. Other people program it now. Is a physicist who always thinks in terms of complex numbers. And so he's saying the answer is 1 if the real part of lambda is positive. What's the real part? Well, don't worry about it. If lambda is a real number, the real part of lambda being positive means lambda itself is positive. Which, yes, okay, lambda, we've talked about this before, has to be positive. That's got to be the case because of that negative sign there for this to be an exponential decay when t is positive. For the graph to look like that, and for the integral to converge. And it converges to 1. So it is a probability density function. We can use it to find probabilities. Today, I'm going to denote probability symbol by PR instead of just a P. And the reason for that is I'm going to have another variable the last 15 minutes of class that I'm going to call P, and I don't want there to be too many P's. So I'm going to use PR for probability today before we've used P. The book just uses P, I believe, I think, for probability. If you want to find the probability that the variables between two numbers A and B, the big idea that you can apply to other examples is that you integrate the PDF from A to B. This is a PDF probability density function, and it's going down there for that integral. That's how you find probabilities. For this example, that is the integral from A to B of lambda e to the negative lambda t. I'm assuming A and B are positive here. 0 is less than A is less than B. I could put less than or equal to there, I guess. Do the integral by hand. Antiderivative is negative e to the negative lambda t. I just did that in my head. T goes from A to B. Simplify, you'll get negative e to the negative lambda b minus negative e to the negative lambda a. 2 minuses make a plus. The simplest way to write this is e to the negative lambda a minus e to the negative lambda b. Okay, as one example, and if I pick particular numbers, I can evaluate the value of this function. So for example, if I pick a to be 1, b to be 2, and lambda to be 1, just as an example, I'm going to get e to the negative 1 minus e to the negative 2. And that is e to the negative 1 minus e to the negative 2. It's about 0.23. About a 23% chance that if lambda is 1, that you're going to get a value for the variable between 1 and 2. Is that really right? We can simulate it and see if it seems right. We did this before too. First of all, to confirm the PDF, we could go PDF exponential distribution, square brackets, lambda, comma, t. This is going to confirm the formula right there. The true means effectively t is less than 0. It's the other condition. I don't know why it puts it in there as true. Ignore the true, it's just when t is less than 0. And RandomVariate, I showed you this before as well, we'll do simulation. RandomVariate, but variate exponential distribution. Let's pick a value of lambda like 1. I don't need the comma t, I don't need the PDF here. If I want 100 simulated data values, I put a comma 100. There's 100 simulated data values. What I'm just predicting by this probability calculation here is that 23% of them, approximately, are between 1 and 2. I could try counting, okay? Yeah, this is between 1 and 2, this is between 1 and 2, this is, etc. Should be in the ballpark of 23 of them. Anywhere I would guess between 20 and 26 might be reasonable. I could do another simulation, get another 100 numbers. Once again, somewhere close to 23 of them should be between 1 and 2. I won't take the time to double check it. Guess we could go to 10 and see if it's close to 2 or 3 of them. 0 in that case. Do it again. Here we got 3 of them between 1 and 2. Okay, it varies. The bigger your sample size is, the more accurate it's going to be. Okay, so a sample size 100 would be better than a sample size 10. I also showed you this before, that if you, for example, store this in a variable, I'll call it data, that you could plot the data with number line plot. And it's good to maybe also plot the PDF. The PDF, if lambda is 1, is e to the negative t. And if I plot that along with number line plot data, and I think there's an extra thing I need to do here to make the spacings 0, to make these data points be on the horizontal axis. Then we get a graph like this showing the density function and showing the data. Definitely denser where the PDF is higher and less dense where it's lower. Once again, about 23 or so of the dots should be between 1 and 2. That's what we're trying to model, and we can simulate it. Of course, in real life, you'd want to have real data instead of just simulated data. But the simulated data can help understand the concepts and confirm the theoretical calculations that they seem right. That's what the simulations can do for you. They can also help you understand what's going on in complicated situations where maybe formulas are unclear. Okay. We also know that from the PDF, we can figure out the CDF. PDF, you want to write it down, stands for, again, probability density function. CDF stands for cumulative distribution function. The book just calls it a distribution function, which is fine. It's a cumulative distribution function as well. It's keeping track of accumulated probabilities, you might say. Capital F of t. Here's an equation that's always true no matter what the situation. It's the probability, again, I'll use PR for probability, that the random variable, in this case, capital T, is less than or equal to the given number, in this case called little t. That is an abstract version of a formula that always works. Though in different situations, we might call the variables different names. Maybe little x and capital X instead of little t and capital T. So this always works. It even works with discrete probability as well, which we're not doing. How do you find this? In the abstract, you're effectively using this equation with a equal to minus infinity. right? Which you can't get less than. Can't equal it either, but don't worry about it. We're effectively using this equation with the a being minus infinity. This is the integral from minus infinity up to what? Up to t. The t here is acting like the b. That's the upper limit of the integral. It is the variable for this function. This should feel familiar. Integral with a variable in the upper limit of integration. Something you could apply the fundamental theorem of calculus to differentiate this, and I will in just a minute here. Of the PDF, use a different letter like tau, f of tau d tau. Again, sometimes people are sloppy there. They use this t here as well, but that's sloppy. It's so sloppy, I don't like doing it. I want to emphasize the true variable here is that upper limit. This is true in the abstract and also in the abstract by the second fundamental theorem of calculus from chapter 6, the derivative of capital F equals little f. Use the same variable in both spots there. Capital F is an antiderivative of little f. That's the point. You can use the integral to abstractly represent the antiderivative, even if this doesn't end up having a simple formula, even if it involves like, Earth or Fresnel or whatever. Could be some function you've never heard of before. It's still true that its derivative is the PDF. For this example, it does work out fairly simple. For this example, at least when t is greater than or equal to 0, you can actually just integrate from 0 to t, kind of out of room here, 0 to t instead of minus infinity. Why? Because our PDF is 0 when t is negative. That's why. I can ignore it. Integral from minus infinity to 0 is 0. Because the function is 0 over there, right? Piecewise formula. 0 if t is negative. So I can just integrate from 0 to t, e to the lambda e to the negative lambda tau d tau. That's going to be negative e to the negative lambda tau. Tau goes from 0 to t. If you plug in the numbers and simplify, what you get is 1 minus e to the negative lambda t, if t is greater than or equal to 0. That is an antiderivative of the PDF. Not the only antiderivative, but it's a special one that has some special properties. One property of which is that it approaches 1 as t goes to infinity. As it should, because the area under the PDF is 1. The probability, if I plug in bigger and bigger numbers for little t here, approaches 1 in the limit as t goes to infinity. The limit equals 1. That's why it's special. Also notice its value at t equals 0 is 1 minus 1 is 0. So its graph starts at the origin and goes up. Has the line at 1 as a horizontal asymptote. Yeah, the graph for this example, I'll put it over here, looks like this. Has 1 as a horizontal asymptote. Technically, it's also defined when t is negative, but it's 0 when t is negative. So technically, it's a piecewise function as well. The fact that the PDF is higher when t is a small positive number and the data are more dense is reflected in this graph by a steeper graph, higher slope. Probabilities are accumulating faster when the slope is higher. Just like they're accumulating faster here when the value is higher because the area under the curve is accumulating faster. With me so far? So far, this is pretty much just review. Now on to new things to try to answer these questions. Have we answered number 1? Well, sort of. We've come up with a candidate distribution. I'm not saying it's accurate for refrigerators, right? And in fact, you look at these numbers, if in this simulation, if time is in years, hopefully this is not very accurate because most of them don't last very long, right? Oh, if time is measured in decades, it's not so bad. Or centuries, I mean, we say it's really good. It depends on how, the measurement unit. Now we want to figure out the mean. What is the mean of the lifetime? Mean lifetime. It's really a center of mass. You could call it a center of mass. And like we called it a center of mass with thin rods, like we called that X bar, we could call this X bar. However, that's actually not what statisticians do here. X bar is the symbol for a mean of data. Data values, actual numerical data. It's not the symbol for the mean of a random variable. It's a good thing, actually. The symbol for the mean of a random variable, a more abstract kind of idea, is a Greek letter, the Greek letter mu. That's a mu. And I love that that's called a mu because it kind of looks like an M and it kind of looks like a U, but it's neither. It's a mu. You got to humor yourself in these things, right? Just enjoy the symbols and that kind of thing to a certain degree. And they're kind of pretty. A mu. Okay. Center of mass, what is that? For thin rods, it's the moment in the x direction divided by the mass, right? Capital M divided by little m. What's the mass here? We don't have a thin rod, do we? Well, a more abstract kind of thin rod. A thin rod of probability, right? Not an actual physical thin rod. Since the integral of the PDF is 1, its mass is 1, because you integrate densities to find masses. And the density integrates to 1. It's capital M over 1. Just capital M. The moment. In fact, in probability and statistics, the mean is sometimes called the first moment. First moment? Yeah, because there are second moments and third moments and fourth moments that are kind of somehow higher order means, which I'm not going to get into. It's the moment. And how do you find the moment? And is it a moment of inertia? Should I think about seesaw as a... Okay, hang with me here. Moment of a point mass is the mass itself times its location. The moment of a bunch of point masses is the sum of their individual moments. The moment of a thin rod is the sum of some infinitesimal moments, where sum means integral. You have to integrate locations times masses. If I'm calling the variable t, the location is t. If I was calling the variable x, the location would be x. What are the tiny infinitesimal masses? They are the quote-unquote products f of t dt. That's like a dm there. Infinitesimal mass. So f of t is a density times a small length. So t times dm is a moment of an infinitesimal chunk. Add those up by integrating, you get the total moment of the entire probability distribution. In general, you have to go from minus infinity to infinity. So in general, it's an improper integral, and it's got to converge if this is going to make sense. For our example, once again, this simplifies. For our example, we can integrate from 0 to infinity instead of minus infinity to infinity. t times lambda e to the negative lambda t dt. This could be done by hand using integration by parts. In fact, I think we did do this exact example back before spring break. Let's see what we get with Mathematica. Integral 0 to infinity t times lambda times e to the negative lambda t. Probably Mathematica will again say, here's the answer, assuming the real part of lambda is positive. When lambda is a real number, that means lambda itself is positive. The integral converges to 1 over lambda. Does that make intuitive sense? Think about the PDF, the distribution. The bigger lambda is, the higher this part of the graph will be, and the lower that part will be because it's still got to integrate to 1. When lambda gets bigger, the graph gets higher over here and it's got to go down faster over here. Most values cluster really close to 0 in that case, if lambda is big. If lambda is big, 1 over lambda is small. The average is small. On the other hand, if lambda is small, this graph has a low intercept. The area under it's got to be 1. It doesn't decay so fast. If lambda is small, 1 over lambda is big, you can have some big numbers more commonly, more often. And you have a bigger mean. So this does make some intuitive sense that the answer using Mathematica, MMA means Mathematica, is 1 over lambda. That does make some intuitive sense. And it is the answer, and it is nice and simple, and isn't that nice? One thing you could do then, if you were trying to apply this in real life, is first of all, you gather your data and see if an exponential model seems reasonable. Some people do that just visually, and they say, yeah, it seems reasonable. Some people try to do it more theoretically. But whatever you do, to figure out lambda, you got to have some data. Maybe you got 1,000 numbers, 1,000 refrigerators, and their lifetimes. The average lifetime is maybe 10 years. Set this equal to 10 and solve for lambda. Lambda would be 0.1 in that case. 1 divided by 0.1 is 10. That would be your estimate for the parameter lambda. And then you try to use that for the future, including for warranties, which is the last thing we'll talk about today, which is the hard part. The real extra hard part. All right, what was the next question? What's the median of t? That's the mean. What's the median? Median of a list of numbers is effectively the number in the middle when they're in order from least to greatest. If there is a middle number, there could be 2 middle numbers that you have to average if there's an even number of numbers to begin with. They're both called measures of central tendency. Which one's more useful? It depends on the situation. If you want to know average lifetimes of refrigerators, because that's useful for figuring out average monetary payments of warranties, or maybe more importantly, the present value of those monetary payments. I am going to relate this to last Friday. Then it seems like the mean is the more important thing to know. On the other hand, if you're trying to describe a data set that's got some really high outliers, for example, net worth, right? There's lots of people with a net worth of 0. Most people, when you're an adult, it's in the thousands. But then you got people like Elon Musk, net worth, what, $500 billion? I'm serious. That's like his net worth. It doesn't mean he makes that much money every year because he doesn't sell his stock necessarily. But that's like his net worth. If your data represents net worth, Elon Musk by himself greatly affects the mean. but hardly has any effect at all on the median because he's just one person. So the median is a better reflection of a typical data value, you might say, when you got high outliers or low outliers, if the numbers go that way. So it depends on the situation. But what is the median in this situation? Median lifetime. Call it T sub MED, T-med for short. It's chosen, it's defined by the condition that the probability that capital T is less than or equal to T-med is exactly 50%, 0.5, or 1/2. So how do you find this? You need to use your CDF. This is the same as capital F of T-med. Med doesn't mean medicine, it means median. T sub median, the median value of T, is chosen so that half the probability is less than it and half is bigger. 50th percentile. In terms of the PDF, half the area is to the left and half the area is to the right. For our example, what does this become? The CDF is 1 minus e to the negative lambda t. So I get 1 minus e to the negative lambda t med needs to equal 1/2. Solve for t med. It's an algebra equation. No more calculus to do. This means e to the negative lambda times t med is also 1/2. Get rid of the e by taking the natural log of both sides. Negative lambda times t med is the natural log of 1/2. By a property of logarithms, that's ln of 1 minus ln of 2. ln of 1 is 0. This is negative ln of 2. And that means t med, the median, is ln of 2 divided by lambda. The negative signs canceled. Is this right? Do simulation to find out, to check if it seems right. We can do the RandomVariate again. Put it down here. And we can, for example, compute the mean of the data and the median of the data. The theoretical mean and median that I got from the theory should pretty closely match the mean and median that I get from simulated data. Lambda's 1 here. So the mean should be close to 1/1, which is 1. And the median should be close to ln of 2, 0.69. Not too far off. Bigger sample sizes, like 10,000, give you more accurate. Yeah, that second one's now close to 0.69. Keep re-entering this. I continue to get more other simulations. In each case, the mean is close to 1, and the median is close to 0.69. Sometimes bigger, sometimes smaller. That gives you confidence that you're doing the math right. How about a measure of spread? Standard deviation related to the variance. You first have to calculate the variance. The variance of the lifetimes is supposed to be a measure of spread. It turns out to be a mean, not of t itself, but of t minus the mean squared, which is kind of a strange thing to do, it seems. Why does that make some sense? When you have data, whether real data or simulated data, sometimes t is going to be above its mean. Mu represents the mean. So t minus mu would be positive. Sometimes it'll be below the mean. So t minus mu would be negative. If I only took the mean of t minus mu, it probably is 0. So to avoid that situation, I square it. How is that? So I'm going to always get positive numbers out for the most part. Sometimes they could be 0 exactly, but how is that a measure of spread? If t tends to be close to mu a lot, then t minus mu will be close to 0. And when you square it, it gets even closer to 0 if it's between -1 and 1 at least. On the other hand, if t tends to be far away from mu, positively or negatively, bigger or smaller, t minus mu squared would be positive, big numbers for those values. That's intuitively why this is a measure of spread. How do you find it? It's analogous to what we did here to find the mean of t itself. The only difference is replace the t with t minus mu squared. That is what you do. I'm not completely justifying that, but that's what you do. Replace that t with t minus mu squared. So you integrate from minus infinity to infinity, t minus mu squared times f of t dt. Now, that's a formula that's the definition of this variance. It's actually not typically used for computations. There's another formula that can be derived from this for computations. But it's good enough for us since we can just use Mathematica. And for our example, once again, we simplify it for our example. So these formulas apply to more general examples. You should be able to use them for more general examples. Other examples, we just can go from 0 to infinity. T minus mu squared, f of t again is lambda e to the negative lambda t. So let's have Mathematica compute that improper integral. It will converge when lambda is positive, which I'm assuming. T minus, what is mu? Mu is 1 over lambda, right? That's what we got from mu for our example. Looks pretty complicated. Let's see what the answer is. The answer is not too complicated. It's 1 over lambda squared. When lambda is positive, which again, we're assuming. Mathematica gives the value of this to be 1 over lambda squared. And the standard deviation, so that's the variance of lifetimes. What's the standard deviation? Standard deviation of the lifetimes is the square root of the variance. In fact, it's common to write the standard deviation as lowercase sigma and the variance as lowercase sigma squared. There's a standard symbol for those things. So it's the square root. For our example, it's the square root of 1 over lambda squared, which would be 1 over lambda, which is the same as the mean. Is that a coincidence? Yes, it's a coincidence. Usually that doesn't happen. But for exponential distributions, it does happen. The standard deviation is the same as the mean. It's nice, it's simple, doesn't usually happen. So if lambda's 1, this is 1. If lambda's 2, it's a half. If lambda's 3, it's a third. By the way, we might also in the simulation want to confirm for other values of lambda that we get the right thing. Like if I change lambda to 2, 1 over 2 is a half. The mean should go close to 0.5. The median should get cut in half as well. It should be close to 0.35. Yeah. So it works for other values of lambda as well. I could also put the standard deviation in here. standard deviation of the data. If lambda is 2, that standard deviation should be close to 0.5 as well. Yes, it is. Doesn't equal the mean for the data, but they're both close to 0.5. The theoretical mean and standard deviation are the same, but not the data. But they're both close. How do you interpret the standard deviation? There's a rule of thumb. Let me just verbally say it, that I wrote it down in the last class, but I'm just going to verbally say it for you guys because we're running low on time. One rule of thumb is that almost all the data, another way to say it is almost all the probability, is within 2 standard deviations of the mean. So if lambda is 1, for example, to be within 2 standard deviations of the mean would be to be between -1 and 3, because the standard deviation would also be 1. Now, exponential variables can't be negative, so the only practical consequence of that is that almost all the data would be between 0 and 3 when lambda is 1. But what is almost all? That's why it's a rule of thumb. It's vague. And you could also generalize it to like almost all the data is within 3 standard deviations or 4. But 2 is kind of like the one that's most commonly used because that seems more useful.